Hi class, we are now in 19.6. This is Gibbs free energy, and we are going to be discussing this for the next few chapters. So this section is more of just an introductory to what it is. Excuse me. This is named after J. Willard Gibbs, and Gibbs free energy is with a capital G. It is capable of predicting if a process is spontaneous at a given temperature. It's a state function, so remember that means it goes from point A to point B, but we don't really worry about how it got there. It's related to enthalpy, which is H, and entropy, which is S, under whatever system that it is that we're studying. So we take a look here, and this is in your book. I'm just going to jump ahead here and show you at 19.7 shows you what the equation is. It's G equals the enthalpy minus the temperature times the entropy. But what it actually is the change in the Gibbs free energy. So we want the change in the system from the change in enthalpy minus temperature times the change in entropy at constant temperature. So this determines if the process is spontaneous. So if it's spontaneous, then we want delta G to be negative. That shows that it would create a spontaneous reaction. This also can determine the direction of spontaneous change of a chemical system, and I'll go more into that. So this pretty much is showing the same on the other page. So this is the general equation, but this is more exactly what we're looking at. We're looking at the changes in a system more than just this in general. So changes in the free energy of this system. This is in your book as well. It's just deriving how this comes together. I'm not going to focus on that. Your book doesn't really explain what free energy is. And so I want to this is why I was a little late on some lecture videos, as I look back at them and I didn't agree with the quality of what they gave me, and I try to fix as much as I can, but sometimes still doesn't work right. So I pulled out some more books and I tried to put together an idea of the more you understand about something, the easier it is to do. So what is free energy? And again, your book to me just doesn't explain it well. So the free energy, it's obviously spontaneous reactions can be used to obtain useful work because it gives off this energy, and with it being entropy, it gets dispersed. This energy gets dispersed. But what if they can use that energy for work, which we've discussed in thermochemistry before, even in 111. Energy can be used directly to move objects of normal size. So for instance, the combustion of gasoline allows a car to move. Because of that combustion, that turns into energy, which allows to move the pistons and so forth. As a reaction occurs, the free energy of the system decreases. So you have in certain reactions, you have a large amount of free energy, but as the system is being used up, that energy also goes away and is replaced, and entropy is produced, but no useful work can be obtained from it. So in principle, if a reaction is carried out to the max useful work that we can get from it, and no entropy is produced, then we would have work at the max equals delta G. So that's, remember, Gibbs free energy. If we could find a way to funnel it into just doing strictly work and not using any of the energy for entropy. Sorry. The term free energy comes from this. This is the energy change, is the max energy available to do useful work. So that's exactly what this means. In reality, though, it's really not true, because in a real situation, we're never going to be able to use that full amount for work. It will, even if it's produced, there will always be entropy. And eventually that work will be changed. It'll show up in the environment as additional entropy. So we can never fully use it the way we would like to. Free work is related to that is work done during a chemical reaction. So let me give an idea, because I want to explain this page. This is very similar to one that you have in your book that's like this. So I want to break this down a little bit. So at the start of reaction, if we look at gasoline and O2, so you can see right here, we have strictly reactions, and we have a lot of free energy that we could use from this potential chemical reaction. And as you see, the delta G goes up and negative. Remember, for delta G to be a spontaneous reaction, it has to be negative. We don't want it to go up. And I said that, where did I say that? Right here. So for delta S to be positive and spontaneous, delta G has to be negative. Okay, so this free energy for this reaction has a very high value. As the reaction goes, and you see the products are created, we are losing that free energy. This decreases. The decrease in free energy appears as either an increase in entropy or as work done. The free energy of the system reaches its minimum value, and that minimum is where equilibrium hits. Once it hits equilibrium, the reaction no longer goes forward because it's in equilibrium. So it pretty much stops producing the reaction anymore, but it goes into equilibrium state. So this potential free energy goes down as the energy decreases, but it is a spontaneous reaction. But when it hits equilibrium, it is now done. And you can see that's where the negative G comes in. It's not a positive value. I show this because you see how this one shows free energy for this Gibbs direction of a spontaneous. It's explaining the Q versus K, and if you need more help on that, I suggest you go back to that chapter. It's not that difficult to review what these mean, but you can see it hits equilibrium at the lowest point, and once it hit equilibrium, the reaction's done. But this is a spontaneous reaction. So what I did is I found another book that explains these, breaking them down separately so they're not on one page. So you can see that that's what's happening on this one. Now, if we go to the other page, so remember now we're looking at this one. The only difference is that this is going into a non-spontaneous reaction. So you can see this is the other one that's attached. So this is from another book. This is a reaction in which delta G is positive, which means it's not spontaneous. There's a small decrease, so it's actually starting here, not up here where we were at. So there's not really a lot of, if anything, there's not really free energy to use on this reaction. There is a small decrease in the free energy. So you see it goes down a little bit and then it hits equilibrium right away. So unlike this one where we had all this energy and this reaction goes quite a ways until it actually gets fully into the products, this one doesn't. The products are here, the reactants are here, and it goes into equilibrium while still in reactants. So basically this reaction went just enough to get into equilibrium with mostly reactants and very little products. This is a non-spontaneous reaction. It would not go on its own. To completely change to products, it would have to have some force push it into this reaction to go. So this mixture consists primarily, and it's a mixture, even if it's mostly reactants, there is products here, but it's mostly, excuse me, it's mostly reactants. So interpreting delta G values, a decrease in Gibbs free energy, so it's below zero, corresponds to a spontaneous process, which is what you see here. And then an increase in Gibbs free energy indicates a non-spontaneous process, which is what I just covered. So you see how the G's go really high and it's positive. And when delta G is at zero, which is a perfect example what we can see here, it's equal. Delta G is equal to the equilibrium. It's hit the equilibrium state. So what happens in the free energy of a solution? Free energy and entropy are also relevant in the formation of solutions. For instance, what about entropy? Entropy works in solutions because it disperses into ions. So there's more disorder to it if these compounds dissolve. So for the dissolution of ammonium nitrate in water, that's highly endothermic and it's used in cold packs. So as it disperses, it's pulling the energy into it and it's making it cold. So a positive value of delta H indicates it's endothermic, for one, indicates the total energy needed to separate the particles is greater than the energy released by the solvation. So that's saying that it needs more energy than what the energy is to release it into solvation. So if this is positive, how does this still occur? This occurs because once the particles do dissolve in solution, they become completely dispersed. And so the dispersal, the spreading out, the entropy is really high. That allows this to be a spontaneous reaction. So remember, one can be negative as long as the other one's, one can be positive as long as the other one's negative or greater value in the opposite sign. That indicates it can be a spontaneous reaction. It'll occur. So this increase in entropy is still greater than what the enthalpy is. So to overcome the positive enthalpy changes, the dissolution of many solutes, it has a very large value of entropy. So a process will be spontaneous when delta G is negative. Delta G is negative when delta H is negative and delta S is positive. That's an exothermic and more random. And delta H is negative and large, but delta S is negative but small at low temperature. Remember, that has to do with heat now. The heat going into a cold room will disperse that energy, excite those molecules even more than a hot room. Delta H is positive but very small. and delta S is positive and large. So it'll still override the delta H at high temperature. Delta G will be positive when delta H is positive and delta S is negative. The entropy is never spontaneous at any temperature. So this one will never be, because that's positive, which means it's endothermic, and this is less disorder. So we don't want that one. And delta G equals zero at equilibrium. So here just gives you some more examples of what I just went over, and some examples of actual reactions that have occurred or occur. So let's take a look at this. Which statement is true regarding the sublimation of dry ice, which is solid CO2? If you've never handled dry ice, it is very endothermic. I have burned my hands. I had freezer burns. I used to have to, so if you go into organic, you will use a rotovap, and a rotovap uses dry ice. It's a vacuum to pull off solvents. And I used to, you have to handle dry ice several times a day, and not being very smart at the time, I would do it with bare hands. And if you've ever touched dry ice, it is very, very cold. I used to end up with freezer burns till I finally got gloves. So it's very endothermic. But if you look at it, you see the entropy. These gas molecules are dissolving. It's a solid. It goes right to sublimation, means that it goes right from solid to a gas. It skips the liquid layer. And that's what's happening. What you see, that smoke, is actually gas. So the entropy is very high for this. So if we want to take a look at all of these, which one would it be? So the easiest one is understand what you're looking at. You don't have to break down everything, but understand a few things over what we've covered. So I'm going to pick entropy. Entropy has to be positive, because just looking at that picture, you can see that it's really dispersed. So if I pick something here that's positive, I only have two of them. And now the other thing is that enthalpy, it's cold. It's very cold, which means, but if you didn't know that, you probably wouldn't be able to determine that. I know personally, because of all the burns I had on my hands, that it is positive. If I'm right, let me make sure I'm right. Yeah. And delta G, oh, I'm sorry, I wrote this wrong, is positive? That doesn't look right to me, but it is, I guess. So it's endothermic, but it's really got great amount of entropy because of how it disperses. So delta G is positive at low temperatures and negative at high temperatures, because it's really not going to do much at that point. So this would be A. All right, so let's do a review. Gibbs free energy for a system is defined by several related equations. This is the basic definition, but we're going to start looking at it as in standard state. That's why I don't have any examples for you here. I will later on. And this is basically the definition. What we would look at is in change. We're looking at the change. We're interested in the change at a specific temperature. Gibbs free energy is defined as a state function. So we only care about initial and final. We don't care about what goes on in between. We use enthalpy, and we look at entropy as well. And that will help us determine, is delta G over more than zero, less than zero, or at equilibrium. And that's it.